So let's go ahead and look at how we can use the unilateral z transform to solve a difference equation. We're going to examine specifically what we call a first-order recursive system. And we'll see why we call that problem this title here in just a second. The difference equation that we're going to look at is this: y of k minus rho y of k minus 1 equals x of k. So we call this a first-order recursive because this contains a y of k minus 1 term. So this difference equation contains a time-delayed version of y of k, and it's proportional to a constant rho times it. So there's not only just y of k, but also a delayed version of y of k. So it's first order, there's just one delay in the output y of k. So this is the difference equation we want to analyze, and we want to solve it, and we're going to solve it for a specific value of x of k, namely the input minus 50 times u of k minus 7. So this is a signal that turns on at time k equals 7, and it turns on by equaling negative 50 for all time greater than or equal to k equals 7. We're going to assume that rho is equal to 1.008, and we're also going to assume an initial condition of y at time minus 1 is equal to 20,000. So these are all givens of the problem, and using these givens we are going to solve this difference equation. So the way we're going to do that is we're going to take the unilateral z transform of the difference equation, take the uzt. So term by term, we can take the uzt of this difference equation. Y of k turns into y of z. And then we have minus rho. Rho is just a constant number. Now I need to take the unilateral z transform of y of k minus 1. If we go back and look at our table, that's easy to do. This is just equal to y of minus 1 in the time domain plus z inverse times y of z. So we're just substituting in that property of the unilateral z transform time shift theorem, and then all of this is equal to x of z, because x of k in the time domain is equal to x of z in the z domain. If we rearrange a little bit and multiply things out, we can rewrite this as y of z, if we isolate y of z, is equal to x of z over 1 minus rho z inverse plus rho times 1 y of negative 1 over 1 minus rho z inverse. So I can solve for y of z in the z domain as this quantity. If you look at these two pieces, really what we have here are two different terms. This term right here is what we would call the forced response, because this part is due solely to there being an input x of x into the system. So this piece right here is what we call the forced response, and this part right here is what we would call the natural response of the system, because it is due solely to the initial conditions of the system. So the initial conditions determine the system natural response, whereas the actual input determines the forced response. Now we actually know what x of z is equal to. We don't know what it is yet, but given x of k right here, we can actually go ahead and solve for what x of z is equal to and then plug it into this equation. So if we go to our table, we can know that the unit step is equal to z over z minus 1, which is equivalent to 1 over 1 minus z inverse. My x of k isn't equal to a unit step, but it's equal to a scalar times a time-delayed version of a unit step. So using this property, we can see that x of z is equal to negative 50, just the constant. It just comes along like constants always do with our linear transforms, times z to the negative 7, because I really have a unit step function that has been delayed 7 samples, times the transform for the unit step, which is 1 over 1 minus z inverse. So using my table and my properties of the z transform, we can easily write down what x of z is, and now I can come plug it into this equation over here. So if I do that, I now have that y of z is equal to minus 50 times z to the negative 7 over this quantity, plus 1.008 times 20,000 over this quantity. So I've gone ahead and substituted in the actual value for rho that we were given in the problem. So I'm trying to solve this difference equation. What I really want is y of k. I now have an expression for y of z, but what I really want is y of k. To get y of k, I can go back to the time domain, and the easiest way to do that is to break this expression for y of z down into pieces using partial fraction expansion. So I can actually write this as a times z to the negative 7 over 1 minus z inverse, plus b times z to the negative 7 over 1 minus 1.008 z inverse, plus 20,160, which is just the product 1.008 times 20,000 over 1 minus 1.008 z inverse. So I can actually write y of z as these three different pieces, and all I need to do is solve for the constants a and b. So that's pretty easy to do. We can go ahead and do that now. We can solve for a using partial fraction expansion by evaluating this quantity at the point z inverse equals 1. So if you plug in z inverse equals 1, you end up with this ratio. You plug this into your calculator and you get 6250. Similarly, I can solve for b by evaluating this quantity at the point z inverse equals 1 over 1.008. So if we plug this into our calculator, we get this, which is equal to a negative 6300. So now that we've solved for our unknown coefficients in the partial fraction expansion, I can write y of z as 6250 times z to the negative 7 over 1 over 1 minus z inverse minus 6300 times this quantity plus the quantity that I had before. So now I've completely decomposed y of z into three pieces, and each of these pieces is now easy to invert back to the time domain. So I can write y of k is equal to 6250 because the constants just come along for the ride. This is just a unit step function that has been delayed by 7 samples. So I have a unit step function that's been delayed by 7 samples. Minus 6300 times 1.008 to the k minus 7 times the unit step at k minus 7, because that's exactly what this corresponds to in the time domain, plus 20,160 times alpha to the ku of k, where alpha is 1.008. So this is the final answer. I have solved for y of k, I have solved the difference equation, and I did it by using the unilateral z transform. I took my original time domain difference equation into the z domain, used algebra to manipulate my expression to solve for y of z, and then I inverted that y of z expression back to the time domain to solve for y of k. And you can use this approach to solve any type of difference equation. Depending on the order of the difference equation, the algebra you have to work through might be a little bit more tedious or complicated, but this strategy of using the UZT is a really good one to use when you are trying to solve